This is section 4.9 on the topic of one-to-one transformations and inverse transformations. So, as you might guess from the title, we're talking more about these transformations. We want to start out with the basic definition here. A transformation T is called one-to-one. See, that's a very important quality, having a quality of being one-to-one. Transformation T is called one-to-one if each element of the range is the image of just one element in the domain of T. Right, so I've drawn little pictures here of the two possible situations. A one-to-one transformation has this sort of look, that if you start with two different inputs, you get two different outputs. A case of something not being one-to-one would be a case where you start out with two separate inputs, vector u and v, but they both map to the same element in the codomain, in the range, right? T of u equal to T of v. So this is what we mean by one-to-one. If the inputs are different, the outputs are different. Any given value in the range was mapped from just a single element in the domain. An alternate definition of this would be to say that if having equal outputs, equal range values, T of u and T of v, if that implies that u and v are equal, then T is one-to-one. Right, this is saying if I start out with in the same place here, in order to be one-to-one, I must say that I really started in the same place. The u and the v must have been the same place that mapped to this one place. Right? So that's an equivalent definition of one-to-oneness. And already thinking about the title of this section, one-to-one transformations and inverse transformations, we might see why this one-to-one property is pretty important. If I wanted an inverse, something that goes back from the codomain to the domain, back from the range to the domain, right? I want this to be able to tell me, given any image value over here, what was the specific domain value that mapped to that? Well, if there were two different ones that map to that guy, I can't invert this, right? If I tell you, oh, this is the place in the range that I want to find the inverse of, right? See the domain that mapped to it, the domain element that mapped to it. I can't tell you which one mapped to it. It could be both, and that wouldn't be a well-defined transformation. It'd have multiple values. So let's move down a little bit. Just a quick example of something like this that you've probably seen before. The function f of x equals x squared, this is not a one-to-one function. This just takes r1 to r1. Values of x in r1 go to values of x squared. Still just scalars in r1. But this is not one-to-one. For example, f of negative 2 is the same as f of 2. They both equal 4. But those inputs themselves were not equal. Right, so here was a case where we had equal outputs, but it did not imply that the inputs were equal. The inputs were actually opposites. So this is not one-to-one. Something like f of x equals x cubed, well, notice if we wanted to test is this one-to-one, we might say, okay, well, assume you have two equal output values, range values, f of a and f of b, they're the same. Well, f of a is just a cubed and f of b is just b cubed. Here you can actually take a cube root of both sides and see that there's no other option. A must be b. So that implies that if our function values were equal, our input values must have been equal. That's this alternate definition. That says this is a one-to-one transformation. What would have happened if we ran this little argument in the x squared case? We'd have a squared equals b squared, which taking a root means, or even maybe solving it differently, means a squared minus b squared equals 0, which gives us actually two options, a equals b or a is negative b. So it is not necessarily the case that having equal outputs meant the inputs must have been equal. In this case, they could be equal or opposite. So that's why this guy is not one-to-one, but this guy is. Okay, let's see a theorem here. A linear transformation T is one-to-one if and only if The kernel is the set containing just the zero vector. Remember, the kernel is just the set of all vectors that map to the zero vector under this transformation. We know, we've seen a theorem, we know the zero vector is always in the kernel of any transformation, any linear transformation. Here we're saying it's the only vector in the kernel. Any other vector won't map to the zero vector under T. So let's show this is true. Let's first assume T is 1 to 1. Well, if we do that, then we know the kernel of T is all vectors, let's say it this way, all vectors V such that T of V equals the zero vector. That's the definition of kernel. But keep in mind, by one-to-oneness, we know for a given zero vector in the range, there is only a single vector. In that kernel, right? One vector that maps to the zero vector. That's by the definition of one-to-oneness. If we're saying what vectors map to the zero vector, there can be only one. If we're a one-to-one vector, there can be only one that maps to any given vector in the range. So there can be only one vector V in the kernel. Well, we've already said, we've seen in a previous section, that the zero vector is always in the kernel. So that must be the entire kernel. There's only one vector. We know the zero vector is a vector in there. It must be the only one. So the kernel is the set containing just the zero vector. So that's if we assume that that our transformation is 1 to 1. We can show the kernel is just the zero vector. What if we work in reverse? What if we assume the kernel is just the zero vector? Can we show the transformation is 1 to 1? Well then, let U and V, let's consider whether T of, just following this definition, this alternate definition, whether T of U equaling T of V implies that U equals V or not. Let's see. Consider T of U, an element in the range, equal to another element in the range, T of V. Well, by linearity, we can move all this to one side, and we get that T of U minus T of V would be the zero vector. Well, that means that, again, by linearity, according to this, we know that U minus V, since it's mapping to the zero vector, that tells us U minus V, let's write it over here, is in the kernel. But we already know the kernel in this case is assumed to only be the zero vector. So that vector U minus V that's in the kernel, it must be the zero vector, which implies, adding the V back over, that these vectors were the same all along. We started with the assumption that we had equal images. It ended up being the case that we actually had to have equal inputs, right? Equal domain values that produce those images. So it does follow from having equal images that the inputs are equal. That means this is 1 to 1. That's our alternate definition of 1 to 1. Fit it in there, okay. Let's look at another theorem here. So that's a big thing to absorb right away, that a linear transformation T is 1 to 1 if and only if its kernel is the zero vector. Right? This is a big statement for us. A linear transformation is 1 to 1 if and only if the only thing that maps to 0 under T is 0. That's what this is saying. Let's look at this next theorem, 4.35 in your textbook. A linear transformation just taking Rn to Rn, so a very specific type of linear transformation, represented by a matrix A, right? Any linear transformation taking a subspace of Rn to another one can be represented by a matrix A. We're going to say this linear transformation represented by A is 1-to-1 if and only if A is non-singular, a non-singular matrix. In a case like this, a transformation T defined by one of these transformations AX, A times X, is called a non-singular transformation if its representative matrix is non-singular. So if we say that the A is non-singular, we might just call the transformation itself non-singular. But let's prove this, that this transformation represented by matrix A is 1-to-1 if and only if A is non-singular. How are we going to do this? Let's first assume, again, like we did in the last one, assume T is 1-to-1. That tells us right away that the kernel is just the zero vector, which, remember, we defined the set containing only the zero vector, we define its dimension to be 0. So the dimension of this kernel, which you might remember we called the nullity of T, is 0. But remember what we talked about in the last section, that the dimension of the kernel really tells us a lot about the dimension of the range, right? The dimension of the range plus the dimension of the kernel we said equals the dimension of the domain. Right, so if the dimension of the kernel, the nullity, is 0 here, it really means that the dimension of the range equals the dimension of the whole domain of T, but in this case, remember, the domain was Rn. So the dimension of Rn is n. Well, the domain of a transformation defined by matrix A is really just the output values that multiplication by A can cause. So we can say here that, let's think about this, the dimension of the range is really the dimension of the column space of A. But that's the same as the dimension of the row space. Dimension of the row space or the column space, we define that to be the rank of A. And I've recalled some facts from theorem 4.18 about all this stuff to help us out here. If rank of A equals n, that is completely equivalent to saying that its determinant, A's determinant, is not 0, so A is non-singular. So this is exactly what we were trying to prove, that this, this is one direction of it, that if the transformation is 1-to-1, then this matrix A that represents the transformation is non-singular. If we work in the other direction, start out by assuming A is non-singular. Then what can we do in that case? That tells us, again, using that theorem I have written out on the side here, that rank of A is n, which implies, right, the dimension of this n by n matrix tells us, well, I should say it this way, if the rank of A is n, that tells us the columns form a basis for our n. Well, if they're a basis, that means the columns are linearly independent. Right. Well, then that tells us about if the we have n columns of this matrix A, they're all linearly independent. That tells us about the dimension of the range of T. Right? Well, that tells us about the dimension of the null space, right? Of the kernel. If we know the dimension of the range itself is n, and the domain was n, well, this guy's got to be 0 to make this, what do we call it, the rank nullity theorem hold true. So if the dimension of the range of T is n, that means the dimension of the kernel is 0, and the only space that has a dimension 0 is the space containing just the 0 vector. Well, here we have it. We have concluded that the kernel of T must be the 0 vector. A previous theorem tells us that T must be 1 to 1, right? If the T being 1 to 1 is completely equivalent to the kernel being the 0 vector. Okay, again, I barely made it fit there, but we got it. There's our proof. Okay, so let's see an example here. Is this transformation T defined by this matrix A 1-to-1 transformation? Well, this isn't so bad to do, right? What can we figure out? All we have to do is figure out 1-to-1-ness of the transformation represented by A has to do with the singularity, whether A is singular or not. Right? A linear transformation from Rn to Rn represented by A is 1-to-1 if and only if A is non-singular. So let's see here. Yeah, maybe we could look here at this theorem. Right, I hesitate to use this theorem because that applies only to a transformation from Rn to Rn, which would require a square matrix. We don't have that here. So I'm going to use this other theorem. A linear transformation T is 1-to-1 if and only if the kernel is 0. The null space contains just the 0 vector. So let's see about that. Let's look at the kernel of T. It's all vectors x such that T of x, which is just in this case A times x, equals the 0 vector. Well, so let's set this up and solve. Let's find these vectors x that do this, right? That's going to be I need 4 elements of this guy to be able to multiply on my matrix. We're saying this has got to come out to the 0 vector. Well, if we set up this augmented matrix, we notice this is already in REF form. So if we were trying to solve this, we would just unpack it again and solve. We'd get x1 is negative 2r minus 3s, x2 is r, x3 is r, and x4 is s. This is what we would get. This is our solution. Notice, though, there is many more than just the 0 vector in this set of x's that we've defined by our equation for the kernel. Right? So it implies 0 is not the only vector in the kernel of our transformation. That means the kernel is not the 0 set, which means the transformation is not 1-to-1. Good enough. All right. Let's see this next example, same idea. Is the transformation T defined by this matrix B a 1-to-1 transformation? Well, notice this matrix is certainly row equivalent to the identity, right? You could just do a couple of row interchanges and get this to the identity real quick. So what does that mean? Well, if we have a square matrix, this is a square matrix, that is row equivalent to the identity, that means it's non-singular, right? According to this theorem we've seen in the past, that means it's non-singular. Well, if our matrix representing the transformation is non-singular, up here we said that means the transformation is 1-to-1. So right away we know. Right? Also, we could have taken the determinant of this, figure out the determinant if that's not 0. Right? We know it's a non-singular matrix, which corresponds to a 1-to-1. A non-singular matrix corresponds to a 1-to-1 transformation. Okay. Right here, though, we were just saying T of x is just this matrix B multiplied on x. Okay. Let's see a little bit more here to end this section. Why do we care about these 1-to-1 transformations? See, there's a close connection to these and all the other sorts of descriptions we've given of systems of equations and really describing sort of the independence or dependence of the columns of a matrix. Right? A very nice fact about 1-to-1 transformations is that they preserve linear independence. Theorem 4.36 in your book says, let T be a transformation taking vector space U to vector space V, and let it be a 1-to-1 transformation. If you have a set U1 through UN of linearly independent vectors, then the image of all those forms a linearly independent set of vectors. Right? The proof here I don't think is so bad. Let's see this proof just very briefly. Right? If we want to show that these guys are linearly independent, we're really talking about taking a linear combination of them and setting it equal to 0 and seeing what that tells us about the scalars in that linear combination. Well, by the linearity of T, we can put this all together this way. Right? Just try to break it back up. It wouldn't be any problem at all by the linearity of T. Right? So if we start out with this identity up here, that implies that T evaluated at CU1 plus CU2 all the way up to CNUN, that equals 0, which implies this vector here, that C1U1, that linear combination there, is in the kernel of T. Right? Because it maps to the 0 vector. But we know this is a 1-to-1 transformation. For a 1-to-1 transformation, the kernel is just the 0 vector, which implies this whole linear combination that we're saying is in the kernel, it must be the 0 vector since it's in the kernel. Since the kernel only contains the 0 vector, if this guy's in it, it must be the 0 vector. Right? But remember, U1 through UN, all these vectors here are linearly independent, which implies if you've got a linear combination equal to 0, every one of those scalars equals 0. That's by the linear independence of the U vectors. Well, what does that mean? All these scalars equal 0 here. Go back up to this identity that we started with. Well, there we have it. Any linear combination of T of U1, T of U2, all the way up to T of UN, any linear combination of those has to have all the scalars, all our C values, equal to 0. Well, that implies that set of vectors there, T of U1, T of U2, right, the image of all our U vectors under T is a linearly independent set. This is a nice fact about 1-to-1 transformations. They preserve linear independence of a set of vectors. Transform the whole set, you still have a linearly independent set of vectors. Okay, so let's talk about invertibility of these things, right? We said these, and this is what the theorem we're going to look at is going to say, that somehow you have to be one-to-one before you can, your transformation has to be one-to-one before you can invert it. If it wasn't one-to-one and I gave you a range value, you wouldn't be able to tell me which domain value it came from. An inverse should definitively tell you that. So let's look at this definition. A transformation T taking Rn to Rn is said to be invertible if there exists a transformation S from Rn to Rn such that S applied to the image of U equals just U, and T applied to the image of U under S equals just U. Right? For every U in the domain R that you started with, Rn that you started with. That's a basic definition of inverses, right? It's kind of undoing the transformation under T. S undoes that and gives you back what you started with. Likewise, T does the same in return. It undoes the effect of S and returns the U that you started with. So this theorem here is really getting down to the important idea behind this invertibility stuff. A transformation T taking Rn to Rn is invertible if it is non-singular. The inverse of T is unique and linear and is denoted T inverse. And this should actually be if and only if it is non-singular. Remember, we're talking about taking a transformation Rn to Rn, so when we say non-singular, we should be thinking about the matrix that represents this transformation between Rn and Rn, and thinking about that matrix and whether it's singular or not. We're saying you get an invertible transformation if its matrix representation is non-singular, if the matrix that represents it is non-singular. Right? So I would just think about this in terms of all these transformations just being equivalent to matrix multiplication. Right? We know a lot about inverting matrix multiplication. Right? We know this can be inverted if and only if our matrix is non-singular, right? Remember, that was up here. This can be inverted. It's equivalent to saying that it can be inverted. It's equivalent to saying that it's non-singular, right? Non-singular is equivalent to invertibility of a matrix A. This is a big, important fact for us. Right. And just like with the matrix inverse, that thing is going to be unique. And since it's represented by another matrix, right, A inverse, it's also linear. Just like multiplication by this matrix is a linear operation, multiplication by another matrix called the inverse of A is also linear. We do denote that transformation described by, represented by A inverse, we denote that by T inverse, written this way. So let's say it this way, T inverse is characterized by matrix A inverse in this case. Okay, so let's see a big summary of everything we've talked about here. There's a lot of moving pieces, a lot of connecting back to old ideas. Let T of U be a transformation represented by matrix multiplication by matrix A times U. Define the transformation Rn to Rn, right? So we're saying it's going from Rn to Rn, meaning A is an n by n matrix. All the following statements are equivalent. This is pretty similar to what I reminded us of from a previous theorem up here, but now we're viewing it through this lens of transformations. So what do we have here? All the following statements are equivalent. Think about these as statements about this matrix A. T is invertible, A is invertible. T is non-singular, A is non-singular, right? We knew that would have to be the case. We've seen here that if T is non-singular, it's one-to-one. Those two are equivalent statements. The kernel of T is the zero vector in the case that it's one-to-one. We've seen those are equivalent statements. The range of T is Rn. We've kind of talked about that. If we have a one-to-one transformation of this form up here, then that means the range of T, which is really column space of this matrix A has to be all of Rn, because we're saying this matrix is non-singular, meaning it has all independent columns. It's got n of them, so it is actually spanning all of this space Rn. The range spanned by those columns, or the space spanned by those columns, is the range of T, so that's Rn. In this case, when this happens, we say T maps Rn onto Rn. A very specific word implying this kind of one-to-one nature here. If T is invertible, we're saying that's equivalent to saying the inverse is also linear, and the inverse is defined by, oops, not matrix A, but matrix A inverse that we wrote earlier. In the case that it can be inverted, you're just inverting this matrix and multiplying by that instead. That's all we're saying. The inverse of a transformation T defined by matrix A just looks like multiplication by its inverse, matrix A inverse. A couple little examples here to end this lesson. If the transformation is invertible, find its inverse transformation and find the pre-image of the vector 2, 3. So here, you could figure this out pretty quick. Think of this as, this is from two variables, the x and y variables, so that's R2, to a two-variable vector in terms of x and y, so that's R2 to R2. So you can think of it as a matrix multiplication, where that matrix is 7, -3, 5, -2, multiplying the vector xy. Right, that's the same thing that T does to the input xy. It does this matrix multiplication. So here we're saying our matrix A is this guy. And this matrix A is pretty easy to find the determinant of, right? The determinant of this guy is -14 minus -15, which is 1. The important thing is it's not 0. A is non-singular. So this transformation T defined by A is a non-singular transformation, which is equivalent to saying T is 1-to-1, which is equivalent to saying T is inverted. Okay. So let's go ahead and find the inverse. Well, remember the inverse is just defined by the inverse of the matrix A. So I need the inverse of that matrix. The formula for a 2x2 inverse is pretty easy, so I'm just going to write this down. 1 over the determinant times, and let's make sure we get this right. Here, what do we get? Using a quick formula for the inverse of a 2x2 matrix, looks like you get 1 over the determinant times, swap the diagonals, and reverse the signs on the off diagonals. So it looks like A inverse is just the matrix, -2, 3, -5, 7. That means T inverse is just defined by multiplying by the inverse that we just found. So if I want to find the pre-image, the vector in the domain that maps to 2, 3 under this transformation T, all I need is the inverse applied to this 2, 3. This is just T inverse applied to that vector, which is just multiplication times that vector with the inverse matrix of A. So what do we get? It looks like -4 plus 9 and -10 plus 21. So what do we have? 511. So we're claiming that 511 should produce 2, 3 when plugged into this transformation. You can check this. I believe it works. Yep, it works just fine. So you can check this. So 511, we can say it this way, T of 511 must equal 2, 3. And you can check that that works. So 511 is the pre-image of 2, 3 under the transformation T. What about this last one here, part B, transformation T of xy equals 0, comma 2x minus y. Let's unpack that into a matrix again. Let's view what representative matrix we have for this. It looks like we would get 0 for both the entries in the top row and 2, -1 in the bottom row. With that definition of matrix A, notice the determinant of A is 0. That implies T is not invertible. Implies there are multiple vectors xy that produce this, that will map to the 0 vector, right? Multiple vectors xy in the kernel. T is not invertible. T is not 1-to-1. It has a kernel other than just the 0 vector. So let's do another one here. Same, but let's find the pre-image of 1, -1, 2. So let's look at this vector. I think this is the last one. Yeah, this is the last one I have planned here. Okay, so let's work this one out. Again, this is 3 variables, so this is R3 to R3 in this case. But the process is the same. I want to rewrite this multiplication by this application of T to the XYZ vector. I want to think of this as multiplication by some matrix. So what would it have to be? In the first entry, so across the first row, we better only pick up a Y. In the second entry, so across the second row, we better pick up only a Z. And it looks like in the first, we pick up only the first. We've actually discussed this exact matrix before. This is our A. This is very close to the identity, right? It's certainly row equivalent. Just swap some rows and you'll have the identity. And that means A is invertible, implies T is invertible. You could say that being row equivalent to the identity means A is non-singular, which means T is invertible. That's also true. So let's see if we can invert this. Let's see if we can do this. Remember, this isn't really so hard to invert. All I need to do, I mean, you could do it the long way, maybe. Let's just do it the long way. Let's not try to get too clever here. Right, there's our matrix. We said to find the inverse. We augment this with an identity. So maybe I'd be a little bit more clear here. This is our matrix A augmented with the identity. And then we reduce this down to echelon form. All I'm going to do is swap some rows around. So let's see. I'm going to take the bottom row and put it in the first. Trying to make the identity on the left side where we currently have A. I'll put the first row in the second. And I'll finally put the middle row in the bottom. So we have the inverse right away. I claim there's probably a quicker way to write that inverse down just by looking at what this has had done to it compared to get from the identity. You can just undo that to get back to the identity. However you like to think about it is fine. This method certainly works that we just did. But now we know that T inverse, T is invertible. We have now found the inverse. Right, so what does the inverse look like? The inverse transformation should look like ZXY. Right? T inverse of XYZ should just be the vector ZXY. So somehow to undo what we've done to the XYZ in scrambling them up here, what we need to do is we need to take the y, which is in the x component here, and put it back. So what was in the x is going to the y component. Let's see if that's what our inverse says. What was in the x went into the y component. Right, what was in the x goes to the y component. What was in the y component should go to the z. What's in the y component? What's in the y component should go to the z. That's right, the y went to the z. And what's in the z component, sorry, the x component should go back to the z component, which this does. What's in the x goes back to the z. I think I'm saying that out loud makes it sound a lot more complicated than it is. We're just undoing this mix-up, right? This jumble of x, y, and z that started as x, y, z and ended up as y, z, x. Well, if you called this your x, y, z, how would you have to move these guys around to get back to x, y, z? To get back to the right order. Turns out this is what you'd have to do. So if we're asked to find the pre-image of 1, negative 1, 2, this will be easy. The pre-image is just the inverse applied to it. It says what's in our z component goes first. What's in our x component comes next. And what's in our y component comes last. There we have it. That's T inverse of 1, negative 1, 2. Meaning, you can check this, that if we apply T to this guy, to our pre-image, we better get 1, negative 1, 2 back. And you can check that that works. Okay, so that is it for this section. We will see more in 4.10.